So in this video, I'm gonna demonstrate how to solve a complex circular equation. That is an equation which involves a circular function, a complex circular function. In order to do this, we need to use an identity, and that's an identity you can recover from most books of complex analysis. That is, the complex cosine of z is the same as or equal to cosine of the real part of z times cosine hyperbolic times the imaginary part of z minus I times sine of the real part of z times sine hyperbolic of the imaginary part of z. So in this, I assume that z can be written in terms of its Cartesian coordinates, like that. What I do is I substitute this part into my equation, and that gives me this equation, which actually contains a real part and an imaginary part. And so does my right-hand side. So this is the real part of my right-hand side, and we could write I times 0, and 0 would be the imaginary part of my right-hand side. So what I do now is that I equate the real part of the left-hand side with the real part of the right-hand side, and the same goes for the imaginary parts. That's the real part of the equation, and that's the imaginary part. So let's start with the imaginary part. So what values of x and y can result in 0 here on the right-hand side? Well, it might be that y is equal to 0, because we know that the sine hyperbolic function looks like this, more or less. If we have y here on the x-axis, that's actually a little bit confusing, but I hope you understand. So when the argument y is 0, then the function value is 0 as well, and that would render this left-hand side 0. Another possibility is that x here is just a multiple of pi, since we remember that any multiple of pi has the sine value of 0. So those are the two possibilities for the imaginary equation. If we look at the real part here, let's start out with the possibility of y equaling 0. If y equals 0, then cosine hyperbolic would be cosine hyperbolic 0, and that's 1. Since we know that cosine hyperbolic function looks something like this. It's not a parabola, but it kind of looks like a parabola, and it intersects the y-axis here at 1. Now, if that's the case, then our real equation here becomes cosine of x times 1 equals 5. Now this equation has no solutions, because, as you probably know, the cosine function looks something like this. It's periodic, and it has a maximum value of 1, minimum value of -1. So there's no way that this left-hand side could ever reach a value of 5. In other words, y is not equal to 0. So it must be that we can rule out this possibility here. And this one. And we have to move forward with the possible solution of x being a multiple of pi. So let's look at the real equation again. Setting x equal p times pi. That gives us cosine of p times pi times cosine hyperbolic of y equals 5. And now we see that not all values of p will render a true equation here. Why not? Well, as you can see over here, cosine hyperbolic is a strictly positive function. It's never negative. So this is greater than 0. So if p equals, say, 1 or 3 or 5, then this part over here, cosine of p pi, that would be -1. So we would have -1 times something that's positive over here that can never be positive 5. So we would have to exclude the values of p that are odd. So what we should write is that x, not minus x, sorry, x equals a multiple of 2 pi, which would ensure that our cosine part here is 1. Then we obtain an equation which looks like 1 times cosine hyperbolic of y equals 5. And that certainly is an equation that has a solution, namely y equals inverse cosine hyperbolic of 5. And x equals a multiple of 2 pi. So z is a multiple of 2 pi as the real part, and then I times inverse cosine hyperbolic of 5. You can actually evaluate what this number is from the definition of cosine hyperbolic, but that would take us a little too far in this video, and it also leads to a quadratic equation, which is solvable, but we'll leave that for another time.